I'd like to discuss the D flip-flop, and this diagram from Dr. Mealy's textbook, it shows the circuit symbol for D flip-flop. A D flip-flop has a D input along with the clock input. This triangle in the symbol indicates edge sensitivity, and I'll talk more about exactly what that means in this lecture. And the D flip-flop has two outputs, Q and not Q. So Q is just the inversion of output, or not Q is just the inversion of Q. Often, instead of seeing this as Q with a bubble that indicates the inversion, sometimes the symbol is shown like this. We're on the input side. It's the same as what you see above, but you'll see Q and not Q like this. You won't see the bubble when the variable is not Q. These tables describe the behavior of the D flip-flop. This table here is the present state, next state table, and this table here is called the excitation table. They both provide the same information. It's just two ways of looking at the same results. So if we look at this present state, next state table, what it tells us in this symbology that you see here, Q, K in these tables, that's the present state of the Q output. And Q plus, that's indicating what the next state, that's the variable used to identify the value of the next state of the Q output. So when you look at this present state, next state table, what it's telling us that it's telling us that if the D input is equal to 0 and the present state of the Q output is 0, well, the next state of the Q output is going to be 0. And if the D input is 0 and the present state of Q is 1, well, the next state of Q will be 0. And these two rows show us that the case of where the D input is 1, here the D input is 1, the present state of Q is 0, and that means our next state of Q will be 1. And then the bottom row here, when the D input is 1 and the present state of Q is 1, well, the next state of Q will be 1. And if you look at this closely, you can summarize that what this present state, next state table is showing is that for a D flip-flop, the next state of the Q output is always going to equal what the D input is. So you can see here in the top two rows that when the D input is 0, it doesn't matter what the present state of Q is, the next state of Q is going to equal 0. In the bottom two rows, when the D input is 1, it doesn't matter what the present state of Q is, well, the next state of Q is going to equal 1. So we'll just say that the next state of Q of a D flip-flop, it just follows the D input. And you see the excitation table gives the same information. It's just, you can see the columns are put in a different order. You know, the way you would read an excitation table is just, well, if my present state of Q is 0 and I want my next state of Q to be 0, well, I got to make the D input 0. See, that's how you read this table. That you just look here to see, well, in order to get this change to happen between present state Q and next state Q, it tells you what the D input would have to equal. Now, what makes the D flip-flop edge sensitive is that this equality here, the next state of Q equaling input D, it happens at the time of a clock transition. Okay, and there's two types of D flip-flops. There's rising edge. Okay, this stands for rising edge triggered. And there's falling edge triggered. Okay, so FET stands for falling edge. Okay, falling edge triggered. And what rising edge and falling edge are referring to are the edges of the clock. Okay, as we talked about in an earlier class, a clock is typically a periodic square wave. And this transition here, okay, these transitions from 0 to 1, those are the rising edges. Okay, those are the rising edges, and the transitions of the clock that go from 1 to 0, those are the falling edges. So if you have a rising edge triggered D flip-flop, the next data Q will equal the D input at the time of the 0 to 1 transitions of the clock. And if it's a falling edge, you'll have this equality that the next data Q will equal input D onto 1 at the time of the 1 to 0 transitions of the clock. Okay, so that's what rising edge and falling edge is all about. And again, that's what's meant by edge sensitivity, is that the next data Q is only going to change and equal, or can only possibly change, and when it does change, it equals input D at the time of these transitions. Those are what are referred to as the edges. So to illustrate this, let's look at a timing diagram. This is another diagram out of Dr. Millie's book. So if you take a look at this timing diagram, our Q output initially starts at starts at 0. You can see the D input initially is 1 and our clock signal is equal initially 0. And this is an example of a rising edge triggered. Okay, so since it's rising edge, only the 0 to 1 transitions of the clock matter when it comes to the Q output, the next state of the Q output being equal to the D input. So like any timing diagram, you evaluate the output anytime a change in input happens. So the first change we get here is the clock signal changes from 0 to 1. So at that time, since this is rising edge, a rising edge triggered D flip-flop, the next data Q is going to equal D. So you see that's why the Q output here changed from a 0 to a 1, because D was 1 at the time of this rising edge. Now notice the next thing that happens is the D input changes from a 1 to 0 here. But at that time, if you look at the Q output remained the same. And the reason for that is because, again, the only possible time that the Q output can change is on the rising edge of the clock. So the D input changed here, but the Q output remained the same, since we're not at the time of a 0 to 1 transition of the clock. The next thing that happens in time is now the clock here changes from 1 to 0. This is a falling edge. But since this is a rising edge triggered D flip-flop, well, the falling edges don't matter as far as the next state of Q is concerned, so the Q output just stays what it previously was equal to. Okay, and you can see here that the D input changes at this time from a 0 to a 1, but again, that's not at the time, or we're not at the time of a rising edge, so the Q output just stays the same. So then our next rising edge comes at this time, and at that time our D input is equal to a 1, so the Q output equals D at this time, so it just stays a 1 since it was a 1 before this rising edge. And let's see, the next time a rising edge happens is right here, And at this time, at this rising edge, well, you can see the D input is a 0, so that's why you see the Q output change from 1 to 0. So, you know, you should be able to understand the rest of this timing diagram. It's the same process, the same concepts as we talked about for this portion of the timing diagram. You know, again, the key thing to remember is that with an edge trigger D, the Q output can only possibly change at the time of the appropriate transition of the clock. If it's rising edge, it's the 0 to 1 transition of the clocks that matter. If it's falling edge, it's the 1 to 0 transitions of the clock that matter. If the D input changes in between those clock edges, well, the Q output just remains the same. Okay, now with D flip-flops as well as other type of flip-flops, you often have these additional inputs in addition to the D input and the clock input. You'll often have a reset, set, and enable. Reset just means that when it's activated, so when reset is activated, the Q output becomes 0. And when the set input is activated, the Q output becomes 1. Now enable is another input that you sometimes see on a flip-flop, and the enable, when it's activated, the flip-flop will operate. Okay, but if the enable is not activated, the flip-flop isn't going to do anything. It's not going to operate. Its outputs would just remain what they previously were, and none of the inputs would have any effect. So in order for anything to happen, the enable has to be activated. You know, for any of these other inputs, the D input, the set, or the reset, for them to matter, the enable has to be activated first. Now, all of these inputs, reset, set, and enable, they can either be active low, active high, and they can either be asynchronous or synchronous. Active low just means that that input has to be set to a 0. Okay, so when the input, when an active low input is set to 0, the function happens. So, you know, for example, if you had an active low reset and you put a 0 on that reset input, that's when Q is going to equal 0. Or if you had an active low set, same thing, that when you put the 0 on the set input, since it's active low, it will set the flip-flop and it will make Q equal to 1. And if you have an active low enable, well, it's going to take a 0 on that enable input to get the flip-flop to operate. And active high just means you need the input set to 1 in order for the function of that input to occur. So active high reset means you need a 1 on that reset input to get Q equal to 0. Active high set means you need a 1 on that set input to get Q equal to 1. And active high enable means you need a 1 on the enable input to get the flip-flop to operate. Synchronous, a synchronous input does not depend on the clock. So if you have a synchronous input, like a synchronous reset, it doesn't matter whether the clock is on rising edge or falling edge or anywhere in between. If it's an asynchronous input, it will reset as long as it's got the appropriate 0 or 1 on its input. Synchronous does depend on the clock. So a synchronous input it depends on the clock, and it's either going to be depending on the rising edge of the clock or the falling edge of the clock. So if you have a synchronous input for a rising edge triggered flip-flop, well, it's not enough just to activate the input with a 0 or a 1. You also, at the same time, have to have the appropriate transition of the clock to occur. I think the best way to see the difference between asynchronous and synchronous is through a timing diagram. And you know, all these inputs, the reset, the set, and the enable, they can all either be active low, active high. They can all either be asynchronous or synchronous. So let's do an example with a timing diagram that has these various inputs. So here we have a D flip-flop, as you can see, with reset and set. Both are active low, but the reset is asynchronous, okay, so it does not depend on the clock, and the set is synchronous, where it does depend on the clock. And then this is a rising edge triggered flip-flop, so it's the 0 to 1 transitions of the clock that matter. Okay, so you can see right here at this time, you can see right here at this time our active low reset goes to 0, right? 0 right here. Well, since it's asynchronous, it doesn't depend on the clock, so I don't care anything about the clock. Once this asynchronous active low reset input goes to 0, that's going to make my Q output 0. Okay, so my Q output here is going to be 0. Now, before this reset happened, Q was either 0 or 1, but I don't know what it was. I'm not sure what the Q output is until this active low asynchronous reset occurs. So because it's not possible to determine by the information that's given here what Q was prior to that active low reset going to 0, I'm just going to put an X, meaning that I didn't know what it was here. Now you could also assume a value, either 0 or 1, but again, you don't really know, so that's why I think the best way to show this is, again, this X just means we don't know what the Q value was prior to that active low asynchronous reset occurring. Okay, well, the next thing that changes here, the next thing that changes is now the asynchronous active low reset goes high, so we're no longer resetting at this time, and that happens just before this first rising edge of the clock. Right, here's our first rising edge of the clock. So since we're no longer doing an asynchronous reset, at this time the Q output is going to equal the D input. So our Q output is 0 here. Okay, let's see, it's 0 here, and then it goes high. Right, then we have another falling edge of the clock, but that doesn't matter since this is rising edge. And you see all this time where D is changing, the Q output's going to stay the same, right? Because again, the only possible time the Q output can change based on the D input is when we get the appropriate transition of the clock. So the next rising edge isn't until right here. Okay, so right here's our next rising edge. Oops. And at this time of this rising edge, you can see that D input is equal to 0, so our Q output's going to go to 0. Okay, so it's just looking at each of these rising edges here and setting Q equal to D. Now at this time, our asynchronous reset goes to 0 again. So no matter what our what our relationship between the D input and the clock is at this time, because this is asynchronous, it's going to make the Q output 0 at this time. Right? Again, when it's an asynchronous input, it doesn't depend on the clock. So once it's activated, it's going to happen. So it's going to make Q equal to 0. And whoops. Yeah, so you can see like during the time of this rising edge here, during the time of this rising edge, the active low asynchronous reset is activated, so that clock edge isn't going to matter. Let's see, our next rising edge is right there. And at this time, D is equal to 1, and we're not resetting any longer, so the output will go high here. Okay, so now, here's the first time that our set input is activated. Our active low set is activated. So it goes low right here. However, the set input, it's synchronous, so it does depend on the clock. So even though this set input went low here, the output isn't affected. Now, it was high anyway before this happened, but if this Q output had been 0 just before this active low synchronous set went low, it would still stay low, because in order for that set to happen, it not only has to be a 0, but it has to occur on a rising edge of the clock, which it doesn't. See, it happens in between rising edges. So even though this set went low, it's not going to set the output. Okay, so then continuing on here, at the time of this rising edge, D equals 0, and we're not resetting, so Q does depend on the Q value here. Okay, so now it's going to be low, but look what happens here. The set output goes 0 again. So like we said earlier, because it went 0, but there's not a rising edge of the clock, it's just going to stay 0. It's not going to go to 1 until this rising edge, right? Because now we have the set input equal to 0, and also here's the edge of the clock, the rising edge of the clock. So the output will be 0 until that rising edge, and then it gets set, and it will remain set. So that's the key difference between asynchronous and synchronous, is that an asynchronous input, once it's activated, it's going to function, make the Q output go the way it should go right away. It doesn't depend on the clock. But if it's synchronous, it's not enough for just the input to be its active value. It also has to occur during the time of a clock transition.